Swayam Prabha. Digital India. Educated India.
Okay, so now let's discuss the problem set 3. So the first question in problem set 3 is about the formation of hydrate. So as we know, aldehydes and ketones can actually form diols, and the diols are geminal diols. Okay, and so the structure of these geminal diols are something like this, and so you could have R and then H if it's an aldehyde, for example. And so you can actually measure the equilibrium constant, and the way you would do this is aldehydes and ketones actually have a very nice absorption pretty much in the UV visible region, and so monitoring the absorption of the aldehyde, you can actually determine the rate constant. So the way the experiment is done is that you would take the aldehyde and measure the, this is the absorption and this is lambda, and so you would measure the absorption of the aldehyde in an organic solvent. Maybe you can put it in acetonitrile or THF or something and measure the absorption. Okay, and now let's say we start with 1 molar of the aldehyde and measure the absorption. You will get some value. Okay, then you make the same 1 molar solution in water. Okay, so when you do this in water, what will happen, or what may happen, is that the aldehyde will convert, aldehyde or ketone will convert to the hydrate. Okay, so the hydrate does not have an absorption at this wavelength. Okay, so therefore you will find that this absorption goes down when in water. All right, and so by measuring this difference in absorption, you can actually estimate how much of aldehyde has formed the diol. All right, and so you can experimentally determine the concentration of the carbonyl compound, which is what you started with, and you can get the carbonyl compound after you added water. And if you assume that the water concentration is 55 molar or whatever, you can estimate the concentration of water, and the concentration of hydrate will be a difference in these two values. Okay, so this is actually an experimentally determined value, and so you get an equilibrium constant of 41 with formaldehyde. And as the substitution on this aldehyde goes up, and if you form a ketone, the value of the equilibrium constant goes down. Okay, so the question here is, what is the percentage conversion of the carbonyl compound to the hydrated form? Okay, so I have worked out the answer. The way you would do this is you would take the aldehyde concentration and water concentration, and then you, like I told you, this is actually an experimentally measurable value, and then you divide this and you get the K hydration. Okay, so from this K hydration, if you assume that the concentration of water is 55.5 molar, then you can actually find out the percentage of conversion to hydrate. Okay, so the value for formaldehyde, if you work this out, is 99.96. The value for acetaldehyde is 50. This is percent, and for tertiary butyl aldehyde, which is shown here, the value is 19, and lastly for acetone it is 0.14. Okay, so when moving from formaldehyde to acetone, you have completely reversed the percentage conversion to the hydrate. Okay, so one of the ways in which we want to understand this is that, as you know, it's an equilibrium between the carbonyl and the hydrate, and so the position of the equilibrium depends on what groups are attached to C double bond, so which is obvious in the case of formaldehyde, acetaldehyde, and acetone. Okay, so formaldehyde, as we found out, basically it doesn't have any aldehyde in solution in water, whereas acetone hardly has any hydrate present in water. So therefore, like with many other effects, they depend on both sterics and electronics. So the alkyl substituent, as we have as you might have studied earlier, stabilizes this carbonyl compound, and therefore the position of the equilibrium can be altered by adding more alkyl groups on this position. So if you have R versus H, once you replace the H with an R, then the ketone becomes more stable. Okay, so therefore, though the reactant of this molecule, of this equilibrium, which is the carbonyl compound, actually gets more stable, and therefore the population of the ketone increases, and therefore the equilibrium constant is going to change. Okay, so this is an important example of how you can use experimental data to actually make interpretations about the stability of various participants in an equilibrium. Now let's move on to the next question, which is to propose a mechanism of the reaction of cyclohexanone with ethylene glycol, and it gives you this cyclic acetal as the product. Okay, and there's another piece of information that's given, which is that the carbonyl oxygen, if it's labeled, then none of the product had this label in the what has been shown. Okay, so now how does this mechanism go forward? So in general, a mechanism of acetal formation goes in the following way. The aldehyde gets protonated, and after the aldehyde gets protonated, the alcohol, which is ROH, can attack in this, and then you push these electrons back here and you form this kind of an intermediate. Okay, if this loses a proton, then you form a hemiacetal. Okay, so the formation of hemiacetal is pretty straightforward, and now the hemiacetal can further undergo protonation. So one of the ways in which it can undergo protonation is basically to give you back this kind of a intermediate, but it can also undergo protonation at the OH, and that gives you this protonated water, and protonated water can leave and you can generate a carbocation. Okay, so now this carbocation is particularly interesting because it can form a resonance form such as shown here, which is extremely stable because both the carbon and oxygen have octet of electrons. Okay, so therefore this might be one of the reasons why this kind of an intermediate can actually be produced. Now if you attack on this intermediate, if another alcohol molecule attacks, then you're going to produce this kind of an intermediate which can lose a proton to give you the acetal. So if we were to draw this last step with cyclohexanone, if we draw the last step, so you get CO, CH2, CH2, OH, right? So this is going to be your intermediate that is formed with cyclohexanone and ethylene glycol. The remaining steps are the same. So this attacks, it's an intramolecular attack, and it gives you eventually it gives you the product, which is this. Okay. Now, how do we account for the labeled result? So if you notice, when we start with this, with C double bond O being labeled, if you start with this oxygen which is being labeled, then you will find that that particular oxygen is actually in this step here, and it is actually lost as water. Okay, and once the carbocation is formed, there is no exchange that happens which will give you the intermediate that you look for, which is, even if water exchanges, it's going to go back and it's still going to continue to be labeled, and the water that is being kicked out is going to be labeled. Okay, what it tells you is that there is no exchange of oxygen between this ethylene glycol oxygen and this carbonyl oxygen. Okay, and I would say that yes, it is consistent with the proposed mechanism, because in nowhere in the mechanism we propose that the ethylene glycol oxygen undergoes a exchange with the water. Let's move on to the next question. So here, this is something that we've already discussed in class, so I'm going to go through this quickly. So here, I'm giving you a little bit of flavor of NMR. I'm going to have a separate lecture on NMR, so some of you can refer to that. But we don't need too many concepts of NMR here. We just need to understand that the number of peaks and so on, which is fairly reasonable to propose, given the information that we have. So if I look at this NMR spectrum, we have 2 peaks in the aromatic region, and all the other peaks are in the aliphatic region. So we are mainly interested in the peaks at the aromatic region, and keep in mind that the yield of the compound is 94%. Okay, so if I look at the product that can be formed, the product has basically this hydrogen here and this hydrogen here, which is basically two sets of hydrogens, because these two hydrogens are identical. That is, I'm going to color it in yellow. So these two are the same and these two are the same if you look at symmetry wise. So therefore you would see two sets of signals, which is what you see here in this NMR spectrum. So therefore the major product that is formed is actually the para compound. Now in order to cross check this, let me draw out the peaks, the hydrogens of the ortho derivative, and you will find that there are going to be four sets of signals that would be produced if this was the major product. And now if you move on to the next slide, you find that you would expect that you will have four sets of signals that are going to be formed. But in fact, when you look at the NMR spectrum, if you stare at it hard enough, you will see only three sets of signals. Okay, and so the reason for this is that two of the signals are actually merging to produce one signal, and therefore you see only three distinct signals in the aromatic region. But nevertheless, what we can infer is, even if you did not know this, what you can infer that this NMR spectrum does not correspond to this product. It would either correspond to this product or another derivative. But since the mass of this product is the same, it's quite likely that you can suggest that it would be the ortho compound. Okay. Now let's move on to the next question. So here, we have used O18 labeled water, and we've attacked the epoxide with this molecule in the presence of H+. So in the presence of H+, we could expect that this epoxide ring can be protonated, and you form this protonated epoxide. And now this becomes a very, very good leaving group, because it's a neutral hydroxyl group that is leaving. And the center that is over here can actually get activated, or can be a site for attack, or it can also attack at the other position. Now, given the result that we have, that is, there's 99.5% of this and 0.5% of this, it's highly likely that the attack actually happens the way we have shown it, which is given here. Okay, so it gives you this product with the oxygen label on it, which gives you the major product. Now, based on this proposal, what we can suggest is that, when water attacks this disubstituted carbon, it almost seems like the bond that is between carbon and oxygen has already started breaking even before the attack of water, because that would produce a stronger positive charge over here, and that makes this center more reactive. Okay, so this is something that we can infer, that the carbon oxygen bond after protonation has already started breaking, and therefore between these two centers, that is between this center and this center, clearly the more substituted carbon is better suited, better able to accommodate the positive charge, and so therefore this bond breaks in preference to the other one. Now, looking at the labeling data, we can see that the label ends up on this carbon, that is, the water label ends up on this carbon, or it ends up on this carbon. So therefore, we don't find a situation where the label has actually gone to both carbons. So what it also means is that there is no exchange going on between the water oxygen and the epoxide oxygen. Okay, so this also could mean that this attack here may be an irreversible step. That is, once you form this kind of an intermediate, this doesn't close back and kick out water, because if that happens, then what can happen is that this oxygen can also attack here and kick out water, and you will see the label ending up on both the carbons. That is, both of the carbons will have labeled oxygens. So that doesn't seem to happen. So based on this inference, what we can say is that it seems like there is no exchange of labeled water with oxygen of the epoxide. So maybe once the epoxide ring is opened, it is an irreversible process. The second inference is that the regioselectivity of this process is quite high, and the more substituted carbon is the preferred site of attack. The way we might reason this out is that the epoxide ring maybe partially opens up, and there's a partial positive charge on this epoxide ring after protonation, and that positive charge is better accommodated in the more substituted carbon, and therefore that becomes the site of attack of water. Okay. Now let's move on to the next question. So here I have labeled these carbons as 1, 2, 3, 4, 5, 6, 7, 8, and so this is basically a rearrangement or an intramolecular reaction. It's not a rearrangement, sorry. It's an intramolecular reaction where you get this product which is 342.10, which is the same mass as the starting material. Okay. Now what the clue that we have been given is that the peak at 1700 centimeters has disappeared over 2 hours, and so therefore you don't have any ketone in the product. Okay, so the product that is formed is likely the attack of this alcohol on this carbonyl to give you a hemiacetal as shown here, and my handwriting is quite terrible, so I've actually drawn this out using ChemDraw. So this might be a good example of how compounds can actually give you different derivatives like hemiacetal and so on based on the reaction conditions. So notice that under these conditions the hemiacetal does not give you back the starting material, because then you would see that the peak at 1700 would be restored. Okay, now let's move on to the next question. So this is a reaction of cyclohexanone with hydroxylamine hydrochloride. So hydroxylamine hydrochloride has a full HCl molecule on it, so that is what I'm representing here as H+. So the carbonyl compound can actually get protonated to give you this intermediate, and now this carbonyl quite suitable for attack, and hydroxylamine can attack, giving you this kind of an intermediate, and now a proton transfer can occur to give you the protonated water over here, which can then be kicked out by the formation of an oxy. Okay, so you can keep this mechanism in mind because this is something that we will come back to during rearrangements. Alright, now the next question is about reduction with sodium borohydride, and so you get a mixture of 80 to 20. So this is consistent with what we have observed before, that is when you have two methyl groups on the norbornane, you end up with the top phase being hindered by the presence of the methyl group, and so the preferred direction of attack is actually from the bottom phase. So keep in mind that if you don't have the methyl group, then the attack from the top phase is preferred. So nevertheless, you get a mixture of 80 to 20 in this case, and this kind of a reaction is actually a stereoselective reaction because a single starting material can form two stereoisomers of the product, but it forms one of them preferentially. Okay. Now let's move on to the next question. So here is an example of a hemiketal. So this is a ketal derived from cyclohexanone. And so this hemiketal is in equilibrium with the ketone as well as the alcohol. So if I measure the equilibrium constant, then the value that I get for the methyl compound is 2.16, whereas for the ethanol derivative, I'm getting 237. So this difference is about 100-fold, okay, approximately. So what the inference that we can take from this experiment, although there are only two data points, is that the larger the alkyl, the more the equilibrium is pushed towards the right. Okay, so keep in mind that this is Kd, so that means that this is the equilibrium constant for dissociation. Okay, now this is something that we can infer from this data. All right, now in the next question is about pyruvic acid forming lactic acid. So the question here is that write out the relevant structures. So just to give you some perspective here, lactate dehydrogenase actually takes pyruvic acid and converts it to lactic acid, and it uses this coenzyme which is NADH, which is nicotinamide adenine dinucleotide, which is a source of hydride, and at the end of the reaction you actually form NAD+, which is the oxidized form of the coenzyme. And here is the structure of its lactic acid for your reference. Okay, now let's move on to the last question, which deals with the reaction of benzaldehyde and ethylamine. So the general mechanism is shown here. So if you take an aldehyde and react it with a primary amine, then what happens is that if it's done under neutral conditions, then the amine attacks and it gives you this alkoxide. Okay, so you can argue that this alkoxide is extremely unstable and it won't be formed, so which is fairly reasonable. So this is why I put an equilibrium arrow here. And so, but if it is formed, it can actually pick up a proton from this NH and then give you this alcohol. And now nitrogen lone pair can come in and kick out hydroxide. Again, hydroxide is a pretty bad leaving group, and so you could argue that hydroxide will not be formed, which is also again reasonable. And so this is again going to be a reversible reaction. So hydroxide ion is going to come and attack and give you back this intermediate. But eventually, because you have a larger concentration of the amine, it's going to form the imine. Okay, this is again something that we will take up again in the later part of the course, and we will visit amine and enamine chemistry later.